Okay, welcome everyone in the post-lunch session. So we have with us Sara, and she will be continuing what she was explaining yesterday. Over to you, Sara.
Thank you very much. Welcome to the second session of my talks. So as I mentioned yesterday, we are going to talk about some polytopes that we associate to matroids. But first, I would like to give you just a few basic words about polytopes in general. I mean, yesterday in DNS talk, you saw something about polytopes, but anyhow, since I would like to keep my talk self-contained enough, I tell you a little bit. So if we have a finite set of points, let's say V1 to V R in some space like RD, and then if we take the convex hull of these points, what we get is called a polytope. And by convex hull, as you may know, I mean the smallest convex set in RD, which contains these R points. And by just an example, if I have 4 points like V1, V2, V3, and the fourth one, and if I want to take their convex hull, what I get is just this square, right? This is a convex set containing these 4 points in the plane, and this is the smallest one. This can be observed easily, and we can see that its dimension is 2 just by intuition. And if you know what the definition of dimension of polytope is, it is also easy to see because it is just the dimension of its affine hull, the smallest affine set containing this. Anyhow, so now we know what a polytope is, and I don't want to go to details because I prefer to define my favorite polytope here as soon as possible. But before that, I need something about faces also. In general, a subset F of P, our polytope, is called a face of P if we can see F as the intersection of P with some hyperplane H, where this hyperplane is a supporting hyperplane. By supporting hyperplane, we mean that we have a hyperplane H. We know that any hyperplane divides the space into half spaces, right? And then we just name them as H plus and H minus. It doesn't matter. This is just a notation. And if my polytope, the whole polytope, lies inside either of them, then we say that this polytope is a supporting hyperplane. For example, if we work with this polytope above, if I take this hyperplane, okay, so a line in R2 is a hyperplane. If I take this hyperplane H, then we see that the whole polytope is inside one of the half spaces that it generated. So here we have one half space and above we have the other one. As we see, the polytope is inside one of them. So this is a supporting hyperplane. And what this supporting hyperplane gives us is a face, which face, as you see, the intersection of this hyperplane and my polytope is just this edge. So this is a face. But if I take this hyperplane, maybe I should draw it a little bit. Yeah, for example, here, this is again a hyperplane, and it has an intersection with my polytope. But is this intersection a face? No, because this is not a supporting hyperplane, because as we see, the polytope is not inside one of the half spaces. Or for example, if I take this hyperplane, again, this is a supporting hyperplane. My polytope is just in one of the half spaces. And what is the intersection? This is just this point. Actually, faces of dimension 0, which are called vertices. Okay, now we know what is a face, and in particular, vertices of the polytope. And yeah, and also as another example, maybe just here, if I take F to be the convex hull of V1, V2, V3. So we know that the convex hull of these 3 points is just this triangle, right? This is a polytope, but this is not a face of my polytope because we cannot find a good supporting hyperplane that supports this face. Okay, and what else I can tell you about polytopes? As you see in these examples of faces, all of these faces are themselves a polytope again. This edge is the convex hull of these 2 points. Vertex is just the convex hull of itself. And yeah, so faces are polytopes by themselves. And another definition, and maybe the last one here as just an introduction, is the lattice polytope. And in previous talks, I think also by Hannah, you saw this word, but again, I just repeat it, that a polytope P whose vertices, we know what vertices are now, are just lattice points in Z to D, I think I took, yeah. So very natural definition. And now today we want to associate to our matroids that we saw yesterday some lattice polytopes. We'll see how we do this. But before that, I need one object, another concept from matroids. If you remember from yesterday that circuits of matroid were just minimal dependent sets. Minimal dependent sets or minimal non-independent sets. Okay. And now I would like to take some disjoint, let's say C1 to CR. They are in C of M. They are circuits. And if they are disjoint, I take their union and then I call this a cycle of M. So a disjoint union of some circuits of a matroid is a cycle. We should be careful about the notion of cycle in graphs, which is the normal definition that we know all about it. But here is a new expression, cycles of matroids, disjoint union of some circuits, okay? And let's see an example, a very small example. If I take this small graph, just a path over 3 vertices with 2 edges labeled by 1 and 2. This is my graph G. And now I would like to look at its co-graphic matroid this time. If you remember our last example of yesterday, we tried to understand what the circuits of a co-graphic matroid are. Okay, so, and there, if you remember, we were removing some edges, we were separating our graph to a few parts. So circuits were exactly the same as minimal edge cuts. Okay, let's see. First of all, the ground set here is just 1 and 2, two edges we have. And the circuits are minimal edge cuts. It's clear if I remove edge 1, I'm separating my graph to two connected components. So just the singleton of 1. I don't write as a set, just for simplicity. I just write 1. Okay. And the other circuit, the other minimal edge cut is the only edge 2. And that's all. If I take 1 and 2 and remove them, of course, I get 3 points. They are separating, but they are not minimal because they contain 1 and 2, which were some edge cuts. Okay, so I have 2 circuits here. And now let's see what are our cycles. I denote cycles of M by this notation, cycle of M. First of all, note that we always have this, that empty set is a cycle of M. It was not a circuit, but it is a cycle because when I take this joint union of nothing, I can get the empty set. So for sure, I put empty set here. And circuits themselves are cycles because I take the disjoint union of one thing with just itself. So 1 is a cycle, 2 is a cycle. But now here, I have 2 disjoint circuits, 1, singleton of 1 and singleton of 2. So what I get here is the disjoint union, and that's all. So for this graph and its co-graphic matroid, we saw that what are the cycles of M. I hope this clarifies the definition for you. And now it's the time to define my polytope. So the cycle polytope of a matroid, it's clear that we are going to work with cycles of a matroid. The cycle polytope of a matroid M is, I have a polytope, so it should be convex hull of something. So is the convex hull of, now I should give you some points. This polytope should be the convex hull of some points, and I should first see that which space I am in. If my matroid M is over the ground set E, our polytope lies in R to the cardinality of E. So now I should give you some vectors with how many coordinates, the cardinality of E, okay? So what I take as the points or as those vectors are characteristic vectors of cycles of M. So namely, if I have something like this in R to the E, there are some coordinates here, right? And each coordinate is correspond to some element in E. So just in between, if this is the E'th coordinate, then here I have either 0 or 1. If E is inside the cycle, then I choose 0. And if E is not in my cycle, I choose, vice versa, of course. The characteristic vector, as you know. Okay. So having a matroid, we understand its cycles. The cycles have some characteristic vectors in R to the E. And then we take the convex hull of these points. Then we get a polytope, the cycle polytope of a matroid, and we denote it by P psych of M. Okay. Just to understand a little bit better the definition, let's try our previous example again. This graph 1, 2. We took M to be mg star. We understood what are the cycles. The cycles were just here. Now I should associate to each of these cycles a vector. And since here E is of cardinality 2, it means that my polytope is inside R2. Okay, to empty set, we associate its characteristic vector, which is just 0, 0. To 1, I associate the vector 1, 0, to 2, 0, 1, and finally to 1, 2, the last cycle. Both components exist in the cycle, so 1, 1. So in R2, we know these 4 points, their convex hull, and this square that we saw in the beginning. So this is the cycle polytope of this matroid associated to my graph. And as we said before, it has dimension 2. But what can we say about dimension of cycle polytope in general? Is there any formula that we can compute it? Sometimes when we work with 2 different areas, for example, here with matroids, almost from combinatorics, and polytopes from geometry, we would like to translate things in between. And we would like to have some formulas which uses the other language. So if we have some formula for the dimension of this polytope as a geometric invariant in terms of some combinatorics of the matroid, that would be nice. We would be happy to have such a formula. And here I would like to give you some information about this. So this is a theorem by Barahona and Gruchel, which gives us this general formula that dimension of this polytope is the same as number of co-parallel classes of M, whatever it is. But this is something completely related to M. Okay, so here we have a nice totally combinatorial formula for the dimension of our geometric object. I don't want to give anything about proof here, but I would like to at least try to make this expression more clear, and we try it on some example. Okay, so now that we have some motivation, I didn't want to give you a list of definitions with no reason. Now we have motivation and we have some reason to understand this expression, that what is a coparallel class of M, that we should try to compute the number of them. Okay, so let's go to the Matroid world again to obtain some tools to understand this formula better. Okay, and for this purpose, before seeing the definitions, I would like to see something in graph theory again. Let us call these edges. This is E, and I call this one E1, E2, and E3. So this is a graph G. I labeled some of its edges. And you know from graph theory, very likely, that such an edge is called a loop. Very likely you know this. And these edges, these three edges, sometimes are called multiple edges. Sometimes, and here I would prefer this word, parallel edges. All right, edges. So these words are familiar for us in graph world. Okay. But we have a bridge to go from graphs to matroids. And one of these bridge is graphic matroid. If I look at the graphic matroid of this graph G, let's see what are these elements E, E1, E2, E3 there, because we know that this graphic matroid is on the ground set E, the edge set of the graph. Okay, if I look at this loop E, you remember, hopefully from yesterday, that circuits of the graphic matroid are exactly the same as cycles of my graph. And this E is a cycle of length 1. So it is a circuit of my matroid of cardinality 1. And it is indeed called a loop in the matroid, in the graphic matroid 2. If I look at these edges, E1, E2, for example. So these two edges provide a cycle of length 2 in my graph. So it means that I have a circuit of cardinality 2 in my graphic matroid. E1 and E2 is a circuit. I'm just using some definitions from yesterday. And E1 and E3, E2 and E3, every pair are parallel edges in my graph, and every pair provides a cycle of length 2 in the graph, namely a circuit of cardinality 2 in my graphic matroid. Okay. And these three edges, E1, E2, E3, is called a parallel class in MG. Okay, just keep it in mind. And then I give you the formal definition, and then we can compare with what I said here in this example. But for the moment, believe me that it is called the parallel class. And now I give you the list of definitions in general, not only in graphic matroids. In general, for any matroid M, this set, the singleton of E, is called a loop in M if, sorry, we don't put this set, we just say that an element is a loop. E is a loop in M if this set is a circuit. The same as what happened here. You see, a loop in the graph gives us a singleton in the matroid, which was a circuit. Okay, now we understand why we call such an element in this definition loop. Second, a pair of elements are called parallel elements in M if this set of two elements is a circuit. This is the general definition. And as you see here in our example, this was the case. These two parallel edges in the graph provided us a circuit of cardinality 2. Okay, now again, we can understand better why this word parallel has been used for this definition. We have an intuition in graph world. And finally, let's see what is the parallel class. If we have, let's say F, E1 to ER, a subset of E is called a parallel class if it is maximal with respect to the properties that I write here for you. First of all, none of its elements, I mean E1 to ER, is a loop. What does that mean? It means that none of these sets, E1, E2, E3, and so on, is a circuit of my matroid. Yeah, loop means circuit of cardinality. Okay. And second, any two distinct elements of it are parallel. So if you take any two pair, E1 and E3, E1 and ER, any pair, they should provide a circuit of cardinality 2 if you see the second item here. So a set with these two properties and maximal with these two properties is called a parallel class. If we look at our example in the above, without seeing the definition first, I claim that this set of edges is indeed a parallel class. And now you can check the first item. None of these edges, E1, E2, E3, were a loop. This was clear. Okay, check. Any two distinct elements of it are parallel. Yeah. E1 and E2, E1 and E3, E2 and E3, all pairs were parallel. So by our definition, this claim was right. Okay. Now we know what is a parallel class in a matroid in general, and we know what a parallel class means in a special case of graphic matroid, and it has a very close relationship with what we knew about these words in graph theory. Okay, we should not forget why we went in this direction. We were talking about a formula for the dimension of the polytope. But here, I do not see exactly what we learned so far. Here we have some extra co-parallel classes, but I didn't tell you anything about co-parallel classes. But very likely you can guess now what I want to tell you, because you know that this co always reminds us the dual matroid. So if I have a matroid, and if I take its dual, and this dual matroid, I mean, this is a matroid. It has its own loops, parallel elements, parallel classes, everything. So the parallel classes of this matroid are called co-parallel classes of M. Very natural. So if I want to compute something with my formula, I should not look at the matroid itself. I should look at its dual, look at its parallel classes, compute the number of parallel classes of the dual matroid, and then this is the dimension of my polytope. If we just go back to the example, our example here, this polytope. I mean, this is clear that it has a dimension 2, but let's try it with our formula. At least we see that it is valid for this example. So my graph is this path with 3 vertices. I'm going to compute this number of co-parallel elements of M. We said that we don't look at the matroid itself. We look at its dual. But dual of dual, we saw yesterday that it is the same as the matroid itself. So I should look at this matroid. I should compute the number of parallel classes of this. Okay, let's look at this graph. In our definition, I should provide you some subset of E, some subset of 1 and 2, which is maximal with 2 properties. One was that it should not contain any loop. Do we see any loop in this graph? No. And it should have this property that any 2 distinct elements of that set should be parallel. We do not see any parallel edges here. But it does not mean that we do not have any parallel classes, because I can take F to be just the singleton of 1. This set has no loop, and any 2 distinct elements of it, which does not have any, are parallel. So this is a parallel class of MG. And with the same reason, if I take, let's say, F1 and F2, the singleton of 2, this is also a parallel class. And we call these types of parallel classes, which contain just one element, consist of one element, are called trivial parallel classes. But we cannot find more. So we have just these 2 parallel classes of MG. They are the only co-parallel classes of MG star. How many do I have? 2. So our formula also says that the dimension of this polytope is 2. So now we have this nice combinatorial formula for the dimension of the polytope. We saw some definitions from Matroid theory just to understand the formula, and we checked it at least on our small and nice example. Okay. Okay, still we are continuing with our polytope. When we talk about polytopes, if you remember in the beginning, I told you a bit about faces. So here we can ask a question. What can we say about faces of my cycle polytope. For instance, if somehow we reduce the matroid to another matroid, a smaller matroid somehow, and then we take the cycle polytope of that one, do I get a face of the original polytope? Suppose we do something on my matroid M, obtain a smaller matroid somehow, then this is a matroid. It has its own cycle polytope. What can we say about this? Can it be always the a face of the original polytope? So this can be a natural question. And we would like to take a look at this question to see how can we answer this question. So
what do you mean by M prime?
I mean, just another matroid. This is not precise. I mean, I'm just saying that if I do something on my matroid M, obtain another matroid M prime, which is smaller on the smaller ground set, as a matroid, it can have its polytope, its own polytope. Now, can I say that this polytope can be a face of the original polytope? And in the sequel, I would like to provide some operations on matroids and see which one of them can give us faces. Okay.
Yeah, there are few questions in the chat box too.
Okay.
Does parallel class always needs to have an element? Singleton.
I mean, parallel classes where if all elements of your matroid are loops, then the parallel class would be empty, right? But otherwise, since you want, but this is a very special case that usually does not occur. But beside this, since I'm talking about maximal ones with those two properties, whenever I have just one element in the ground set, which is not a loop, then for sure I will get non-empty parallel classes. And then empty cannot be because it's not maximal then. But in just one special case, yeah, one can take it, I think, but rarely it happens.
Okay, then there is another question. If all FIs are singleton, then can we extract this information about matroid or something else? So I think she's talking about the reverse. Can we go from matroid to, from polytope to matroid?
I mean, when I have an equality in my formula, for sure. I mean, in theory, yes, but in practice, of course, yeah, I mean, in theory, yes, because if you have a dimension, then you know the number of co-parallel classes. So if the question was about the reverse, I would say yes. I mean, how in practice it is useful or not is another story. But yeah, but I think maybe he or she, sorry, I don't know, but might mean that if all parallel classes are just trivial ones, what can we say? I mean, there is a notion of simple and co-simple, and later, if our time allows, not today, but in other sessions, we will see that these types have even a name, and they are important ones.
Okay, okay. Please continue.
Yeah, thank you. So now to just achieve some faces of my polytope, I'm trying to understand some operations on matroids, some ways somehow to reduce my matroid. Okay. I give you some actually definitions here again. Deletion in a matroid. First of all, we fix M as a matroid and E as an element of its ground set. By M deletion E, with this notation, we mean a matroid on the ground set E minus E, so we are just dropping one element, whose circuits, we know that we can actually understand the matroid with respect to its circuits or independent sets. And here I would like to focus on circuits, because circuits gives us cycles and we are more near to the structure of our polytope. So then the circuits, I would like to give the list of circuits of a matroid after deletion. What you do here is that you look at the circuits of the original matroid M. Some of them have E as an element, some of them not. You just keep those one which do not contain E. So namely, I'm looking at those subsets of E minus E such that C is a circuit of M. So those circuits which do not contain E are circuits after deletion. Okay. So this is the definition of deletion. But we had an example yesterday, a graph like this, 1, 2, 3, 4, 5. We looked at its cycles, which gave us circuits of my matroid, my graphic matroid, looking at MG. So the cycles, we had 3 cycles here. So the circuits. Now I want to delete one edge, just to recall what were the circuits of my graphic matroid. Again, it doesn't work. I hope I can do something. Nothing works here right now. Okay. Sorry. Okay. Let's just have it here. My mouse does not work. I'm sorry for this. So I prefer to write it down again because my mouse does not work. So the circuits here are just 1, 2, 3. I just wanted to be quicker, but it's worse. 1, 2, 3, 3, 4, 5, and 1, 2, 4, 5. I hope you remember this example from yesterday. So, and now I want to remove this edge 1. Namely, I would like to look at MG deletion 1. By our construction above, what are the circuits of this one? I look at the circuits of M and keep those which do not contain 1. So this is the only one. So after deletion, I just have 1 circuit, and this matroid is on the ground set 2, 3, 4, 5, right? And now I want to show you something else. Very likely you know deletion in graph theory. It's very simple. I just remove this edge. So I have still 2, 3, 4, 5, but not 1. If I take the graphic matroid of this graph, G minus edge 1, and now I want to look at its graphic matroid. It is again for sure a matroid on its edge set, which is 2 to 5. And if I want to see what is the circuits of this matroid, so it is a graphic matroid, I should seek for the cycles of the graph. But here it's clear that you see just one triangle. What is that triangle? 3, 4, 5. So the same. But look at here. At least here it seems that no matter if you first remove the edge from the graph and take the graphic matroid, or first you provide your graphic matroid and then remove, delete an element in the language of matroid theory. But this is not just by an accident. This is always the case for graphic matroid. So deletion, now again, we have a better feeling about deletion because it really fits with what we know from classical graph theory. Okay, so this is the deletion now. The second operation that I want, it was very natural, I think. The second operation that I want to talk about is contraction. Again, I have a matroid M, an element E. By contraction, denoted by this notation, deletion was this, and contraction is like this. Okay, so I remove this. Okay, and now I should consider two cases. This element E can be a loop, a circuit of cardinality 1. Then we define contraction to be the same as deletion. But if this E is not a loop, I need a definition, a different definition that I'm going to tell you here. This is a matroid on the ground set E minus E again. And now I want to describe the circuits of this new matroid. What I take here, I just look at the circuits of M and throw away E from all of them. Some of them contain E, so they are changing in this procedure. Some of them do not contain E, they remain as they were, okay? So it means that I'm taking those, I mean, the best way to write them is that maybe I write C minus E such that C is a circuit of M. But I left some space here because when I drop E from some of them, I mean, they were minimal before, but now maybe there are some containment in between. That's why we take the minimal elements of this set. Okay, so we look at the circuits of M, we drop E from those which contain E, and now maybe there are some containment between these new sets, I don't know, but we just keep the minimal ones and throw away the bigger ones. So then this set is the set of circuits of my new matroid after contraction. Let's see an example, the same example as above. Okay. So we have circuits here. And now I'm trying to contract mg over 1 again. So as I told you, I look at them from those which have 1, I remove 1, and the other one and the others remain as they were. So what we have here is that C would be 2, 3 after dropping 1, 3, 4, 5 as it was, and finally 2, 4, 5 after dropping 1. Here, there is no containment, so I'm not worried about minimal ones. So they are all minimal, so I keep all of them. But you may remember again after seeing this word of contraction from graph theory. So you may think of this operation. I'm contracting this edge. I'm contracting this edge. I'm trying to put this vertex on this vertex. I'm trying to identify them. I'm trying to contract this red edge. Okay, after doing this, what you get is this graph. So I didn't change anything about downstairs, but from upstairs, by contracting this red edge, what happens to edge 2? This also moves with us. So what I get is just this 2. Yeah, it moves with us and become a parallel edge. So this is a familiar operation in graph theory. So it is contraction of G over 1. What if I take the graphic matroid of this one? Again, since it has just elements 2, 3, 4, 5, it is on the same ground set as above. But what are the circuits now? For graphic matroid, we just take the cycles of the graph. Which cycles do I see here? The triangle 3, 4, 5. Another triangle 2, 4, 5. And finally, we also see a cycle of length 2, 2, 3. But what happened? They are the same. Again, it seems that no matter if I do contraction in the graphic world and then take the graphic matroid, or I take the graphic matroid of the original graph and then in matroid language, I do the contraction. Again, this is not just by chance, and this is always the case in graphic matroids. So now we have some intuition for the contraction also. And yeah, I wanted also to give you some exercise. Maybe I just, I don't write it, but I can explain it for you. Just to have some feeling about taking these minimal sets, I would suggest you to take this graph, add another edge 6 here, a parallel edge to 1, and then try the contraction again over 1, and then see what are the circuits. Then you should be careful about taking the minimal ones. So maybe this is very easy, but just for saving time, I don't want to discuss it here, but I think this is a good exercise just to have a better feeling about this operation. Okay. I mean, if you do some deletion over one element E, and then you want to delete another element like F, or first delete F and then E, no different. Also about contraction, this is the case. And also about deletion contraction, this is the case. If we remove E and then delete E and then contract over F, or contract over F and then delete E, it doesn't matter. These orders are fine. You can see it as an exercise. So this seems that it seems to me that, okay, I can take a sequence of these operations. I can delete something, again delete something, then contract something, again delete, contract, contract, delete. So if I do such thing, this third operation occurs, a minor So a minor is a matroid. A minor of M is a matroid which is obtained by a sequence of deletions and contractions. So then we get a minor. And some specific types of minors exist. I don't want to talk about all of them here, just one as an example, which is called series minor. It is a minor, but what we do for obtaining it is going through a sequence of deletions. Deletion with no restriction is allowed, but not all types of contractions. Just serious contractions. What is a serious contraction here? If I do a contraction over an element, and this element is, maybe write it like this. Element E and some F is a co-circuit. So this set of two elements, E with something else, is a circuit of the dual matroid. So if I do such a contraction and deletion consecutively as much as I want, I get a minor, but this is not a general minor. This is a special type that we call it a series minor. So these operations were the ones that I wanted to tell you. Maybe I give you also another exercise. Today, I think we didn't have exercises. You can, as I said, deletion and contraction from graphs and graphic matroids were the same. But what happens if I take the co-graphic matroid? If I remove something from my graph and then I take the dual, it is the same as taking dual and contraction over E. And also the other way around somehow. It is mg star deletion of E. So you may also check this, it is also useful. So for co-graphic matroid, if I remove something from my graph, what I'm doing on the level of a co-graphic matroid is contraction. And if I contract something in my graph, what I'm doing in my co-graphic matroid is deletion. This is also nice and useful for us. But just as the last point, we should not forget our goal. We had a question here that what we can say about faces of this polytope. We said that if we somehow obtain some reductions of our matroids, we do something on matroid to obtain some new matroids, and we take the polytope of that matroid, is it the face of the original polytope or not? We saw some operations to have something in mind, and now we can ask, if we do some deletion, is the cycle polytope of this matroid a face? If we do a contraction, is the cycle polytope of this matroid a face? A minor in general, series minor, what happens in these cases? And what I can show you here is this theorem in an almost recent paper by Tim Romer and myself, that, in a section that we discussed about polytope, cycle polytopes, we showed that in some cases, yes, we get the face. If you do a deletion, if you do a series contraction and co-loop contraction, some types of contractions, but all deletions, you would get a phase. I mean, more precisely, this gives you some affinely isomorphic polytopes two faces. So in these cases, we get really faces. But you may ask, okay, why these special cases of contraction? Are contractions open? I mean, or we don't know anything about them, or really they do not give faces in general? And the answer is not in general. As an example, you can check, or you can just search a little bit about it. If you take C4, the cycle, the square, and if you take P4, the path over 4 vertices, as you see, this edge has been removed to obtain the other graph. Okay, removal from the graph, as I mentioned in the exercise that I gave you, means contraction in co-graphic matroid. And if you take the cycle polytope of this matroid for these two graphs, you see that the one for P4 does not provide a face of the other graph. So contractions do not give faces in general, but deletions always. But some cases of contractions also behave well in this sense. And yeah, I think I can stop here. Today we understood something hopefully about cycle polytopes, their dimensions, something about their faces. And yeah, the next time we will talk about some more algebraic stuff about these matroids and also polytopes. Yeah, and I think I can stop here right now.
Thank you, Sara, for
You're
all
welcome.
these series of definitions. Any questions from the audience? In fact, there is one. Anyways, Aksa just sent the final remark about her question in the chat box. And okay, and then okay. Sara, can you read that question, or should I narrate?
Yes,
it for you?
I'm just reading. Yeah, as I said, yes, when your matroid has only trivial parallel classes, only parallel classes consisting of one element, they have a special name, and of course they are more special matroids, and we know about them much more than the others. As I said, in our next sessions, I'm trying to give you some results that we can assume our matroids to be like the one that you like. So they are nice and important, right? You're welcome.
Any other question?
Yeah, I do have a question. Well, my question is about the matroids. Is a matroid is always going to be a connected graph?
You mean a graphic matroid?
Yeah, exactly.
Okay. You can assume that your graphs are connected because, for example, if you have two connected components here, okay, as you've seen in my lectures, I do not care about vertices that much. What I'm really concerning about are edges, right? And if I have just two vertices here, I just pick one vertex from each component. And then I just glue them to each other. So I do not change anything about, I change vertices, but I do not change edges here. And I do not change the cycles of this graph. So the structure of graphic matrix of this one is the same as this one. And that's why, I mean, it's not necessary, but that's why sometimes people assume that the matroid, graphic matroid is associated to a connected graph. So it's because you can glue the connected components with no, I mean, damage on your structure.
So like if a matroid is connected, then what about the union of two non-disjoint connected matroids? Is it also going to be connected one?
No, I mean, what I explained was the relationship between connectedness of the graph and what happens to graphic matroid. We have the notion of connectedness for matroids, which I didn't tell you because I didn't want to use it here, but it has an easy definition. You can read it from the references, but it doesn't mean that M is connected if and only if the graph, for example, when you're working with graphic matroid, it is connected if and only if the graph is. But there's a relationship here. This is connected by the definition if and only if your graph is two connected, biconnected, if you know what it is.
Oh, yeah.
Okay, but
Yeah.
you have, yeah, but this joint union of matroids is also defined. And if it is not connected, if your matroid with this definition that I didn't mention it here, if you have R connected components, then you have disjoint, this is used for disjoint union of matroids. So this also exists.
Okay, thank you so much.
I could be useful for me.
Okay, there is one question, 1 to 3 is the same as 3 to 1. Yeah, orientation doesn't matter.
Yeah, because
there is
it was
one.
just a notation. Since I was in lack of time, I just tried not to write 1 and 2 and 3. I just chose 1, 2, 3. So to be more precise, you should write this really. No matter.
Yeah. Is there any question from IBA Karachi side?
Is there any question?
Oh, okay. Please go ahead.
I just want your comment on the zero-dimensional cycle or matrix. Something that has zero dimension. Can you give some example of that?
Sorry, repeat again. Zero dimensional what?
I just want your comments on zero-dimensional matrix or zero-dimensional cycle.
Zero dimensional, right?
Your dimension of what? I didn't get the question, unfortunately. I'm sorry.
अच्छा मेट्रॉइड के लिए भी डायमेंशन डिफाइन नहीं किया है आप पॉलीटॉप की बात कर रहे हैं पॉलीटॉप की बात कर रहे हैं yeah Sara she is asking is there some cases where we will get zero dimensional polytope cyclic polytope
zero dimensional, I mean
cyclic polytope.
Yeah, I mean, if I take just, for example, I mean, of course, it can rarely happen for sure, but because zero dimensional means that you should have just one point as the polytope, yeah? And if I take this graph, just one edge, then I take its co-graphic matroid, okay? Now, if I take the co-graphic matroid of this one, the cycles would be empty sets. And no, I think the only case, no, here you get an edge as the polytope. This was not the example. This is one dimensional. I think if you take just the graph, if it is just one vertex which has no edge, yeah, then the cycle is just maybe empty set. And yeah, just in this case, it is not an interesting case. So always we have, yeah, I think Yeah, I think this has also some relationship with the other question that someone asked before, that if the parallel classes could be empty, because yeah, in that case, I think this is only the case. Usually we have some trivial parallel classes in the dual. Let me just have as a summary to this answer, in interesting matroids, not.
That is the best answer, I think.
Yeah.
Yeah. Is there any other question from IBA side or from here? Sarah, I was just curious about, okay, this is very interesting notation of the cyclic polytope, which is associated with the cyclic matroid. So do we have any duality here? Okay, similar kind of term exists for the graphical matroid. I mean, the polytope of the graphic matroid, and then polytope of the cyclic matroid. Some duality follows in the theory of matroid polytopes as well. Do you understand my question?
Yeah, you mean if we have some duals in the level of matroids, do we get duals in the polytope language,
Polytope
right?
level. Yeah, exactly.
You
this
mean
is what
this?
Yeah.
I mean, in general, when we talk about cycle or polytopes of any matroid, we really do not very much about them. We do not. I mean, the results are really little, but even in the case of graphic and co-graphic matroid, I'm not sure yet if they are dual. I don't think in general. No, I think this is not the case always. But it's a very good question. If in some special cases that would be the case, would be very interesting, I think. Yeah, it's a very good question and reasonable.
And one more important thing that would you like to mention, that all these graphical definitions, yeah, you already highlighted these things. So the definition of the minor, deletion, contraction, everything from the graph theory, that translated nicely here. And same is the case for the graphical matroid too, the minor.
Yeah.
Sarah, just a question which is not related to this particular topic. So the neighborhood minor, your other paper with Tim Romer.
Yes.
This is a similar kind of construction, but with some other restrictions.
So it's not related to what I mentioned so far, but if we have enough time in the next 2 sessions, I give a more general structure, which also covers that structure of neighborhood minor.
Yeah,
I give you a structure for any matroid, and if you restrict to co-graphic matroids, we get exactly the neighborhood minor that you mentioned.
Yeah. If this is there any other question or remark from the participants? If this is not the case, let's thank Sarah. Sarah, thank you very much. It was very elaborate. It was very wonderful.
Thank you very much. Thank you for your
Sarah,
attention.
Happy International Women's Day. In fact, now we are going to have a celebration here where we are going to have some cake cutting ceremony, small, just to celebrate the International Women's Day here. We have many women in among us. I hope you would be here too. But anyways.
Yeah, this time it wasn't possible, but I remember last time that I was there, I was for a CIMPA school in Pakistan, not there, but in Pakistan, and it was a great time for me. Yeah, it is a pity that this time I could not be there. I mean, I just, but at least it's nice to see you online, and it's a great job that you are going to do this. I appreciate, and I hope you have a nice time there.
Thank you, Sarah. Take care.
Thank you. Yeah, I'll see you tomorrow. Bye, everybody.
Yeah, there is something